Thank you very much for the invitation to speak. So I'm going to talk about the joint work with Greg Chambers. And let me start with a classical theorem due to Bangert and Thorbergson. 1980, which says the following thing. It will be our theorem 1. If M is a two-dimensional Riemannian surface of finite area, then M contains a closed geodesic. So let me draw a picture. We could be thinking, for example, of R2 with a metric of finite area, and it could look something like this. We have sort of a blob and then one end which becomes thinner and thinner and thinner, so that the area integrates to a finite number. And then somewhere in here, according to Bangert and Thorbergson, it's possible to find a geodesic which closes up. Okay, so we try to prove a generalization of that result to high dimensions. So our theorem is as follows. If M, so one important condition here is that we're talking about a complete surface. Here we will talk about complete Riemannian manifold of finite volume let's say the dimension of M is n+1, and our high dimensional generalization of a geodesic will be a hypersurface, a minimal hypersurface. Then M contains a complete embedded minimal hypersurface which also has finite volume and let me put in parentheses that it's going to be smooth away from a closed set of dimension, Hausdorff dimension n-7. So a closed geodesic is a curve which has the property that it minimizes length if you intersect with a sufficiently small ball and you look at all curves that connect the two endpoints that you obtain with intersecting. And a minimal hypersurface has a similar property with respect to area. If you intersect with a sufficiently small ball and you're in the smooth part, then you will see that it minimizes area among all surfaces with that boundary. So in that sense, it is a generalization, and in case of curves, being complete and compact and having finite length is the same thing. But for minimal surfaces, you can imagine a minimal surface which has something of finite area, but which has parts which extend to infinity. So the hypersurface, the minimal hypersurface we produce here, may or may not be compact. And in fact, there are examples where the kind of the standard methods of producing minimal hypersurfaces, a kind of a min-max sweep-out method, will give you something which is non-compact. It is an open problem whether in this situation you can always construct a compact minimal hypersurface. It is actually not clear to me whether the answer is one way or the other. So it has to be, if it's true, it has to be done in a different way than the way we do it.
But here I think the Casper have, of course, a very particular geometry, and here you don't require.
So here the condition is just the finite area. It is enough to guarantee that sufficiently far outside this will be concave, but that's not true here. Here we don't require anything about the ends, and in fact our theorem is much more general than that. It doesn't require finite volume. I'll give more details a little bit. Later. So let me mention some previous results and some later results as well by other people, which are important to mention. So Gromov has a very interesting paper in 2013. One of the results there is that he has a very interesting condition. He considers manifolds which admit foliations by mean convex foliation by, so I should say Morse foliation. So he allows certain kinds of Morse singularities by mean convex hypersurfaces, and if the manifold doesn't satisfy this condition, if it doesn't have any Morse foliations by mean convex hypersurfaces, then he proves that there exists a minimal hypersurface of finite volume. In case of hyperbolic surfaces, there is a result of Colin, Mazet, Hauswirth, and Rosenberg, where they show that hyperbolic three manifolds of finite volume contain closed minimal hypersurfaces. Let me mention the result by Rafael Montezuma from 2014. Rafael is also, I think, a member here this year. At least I've seen him around several times, where he proved a result. So Montezuma's result and Gromov's result were motivation for us considering this problem. He showed that if the manifold satisfies a condition that it has a region which is with mean curvature pointing inside, it has a concave boundary, and then concave boundary, and it has a certain condition on the ends and thick at infinity. So this condition is kind of orthogonal to ours. In particular, it will have infinite volume. Then there exists an closed minimal hypersurface. Existence of minimal hypersurfaces in non-compact manifolds also plays a role in several other very interesting works. Let me mention just two. So there's a paper by Kitover and Shinju where they analyze entropy of embedding of surfaces in R3 and prove a conjecture of Illman and White, Colding, Illman, and Minikosi White. And what's crucial in their analysis is again to construct minimal hypersurfaces for the weighted Gaussian area in non-compact manifold. And let me also mention a very recent work by Antoine Song, where he proves Gauss conjecture on existence of infinitely many minimal surfaces, minimal hypersurfaces, closed minimal hypersurfaces. But again, what he does is he cuts off certain pieces of the manifold and attaches cylindrical ends, and then he analyzes a non-compact manifold and he constructs infinitely many minimal hypersurfaces in the non-compact manifold. So again, there's an important role of constructing minimal hypersurfaces in non-compact manifold in his work. Okay, so
do I ask, in the compact case, then it always much easier, or what?
yeah, so I'll mention that in a moment. Right, the result of existence in the compact case. So let me now state theorem 3, from which this theorem, theorem 2, will follow. Right. So theorem 3 is more general than theorem 2, and it's also interesting in case of compact manifolds. But I will need a little bit of notation to set up a little bit of notation before I can state it. So the notation that I will need is the following. So if U is some open and bounded subset of our manifold, then we will define something called relative width of the set U to be the following quantity. We will consider all maps F from U into 0, 1. We will restrict to Morse functions from U into 0, 1. And we will look at the supremum of the area or volume of the preimage of T between 0, 1. And we will minimize that supremum among all such functions. So the picture is like that. If you have a, this is your manifold M, you select some subset U, and then you consider functions from U into 0, 1. So the fibers will look something like this. And then you pick the fiber of the largest volume and you minimize. So it's some measure of width or waist or thickness of your space. So of your subset. If M contains set U with relative width of U less or equal than volume of the boundary of u over 10, then M contains a complete minimal hypersurface of finite volume. And let me not write it down, but the regularity is the standard regularity, that it's smooth away from a closed set of codimension 7.
So isn't it the opposite inequality?
Right. So we want the boundary to be small compared to the width. Yes. Yep. So the boundary is much smaller than the width. Thank you.
But now you have the width on both sides. Before you had the volume.
Yeah.
Okay.
Thank you.
Easy. Okay, good.
Thank you. That's it here. Thanks a lot. Okay, so let me make several comments about this result. I'll explain why it implies a theorem 2, and several other things about why it's interesting. So let us see why theorem 3 implies theorem 2. If our manifold has finite volume, and if we pick any point P, and we will consider large balls around the point P, then if we consider, say, balls of radius n and ball of radius n plus 1, then the amount of volume contained in such annuli will decrease because it sums up to 0. And then by query inequality we can pick a geodesic sphere which will have smaller and smaller volume, smaller and smaller area. And so we can find a boundary of a geodesic sphere of arbitrarily small size. Yeah?
Maybe I just misunderstood the statement.
Yeah.
Like in R3, if you take the unity in a cube, doesn't the boundary have volume 2, 8, but the width is 1?
Right, so let me take a look at what I wrote here.
It's correct.
Uh-huh. In R3 you take a large,
No, your statement
seems
seems to be correct.
to be correct.
Your statement looks correct.
So if we
In
take,
a cube in R3,
yeah,
the boundary has volume 8, right? Or 6. 6.
Mhm.
But the width should be 1.
mm-hmm.
I can't see
It doesn't satisfy. Right. Yeah. So you need to be bound. You need boundary to be small compared to. It's the other way around. So if a manifold has finite volume, then we will be able to find geodesic spheres of arbitrarily small size, but the width will not be small. It will be something bounded away from 0, and in particular it will satisfy this condition. Also, if a manifold has sublinear volume growth, if we take a point and we start looking at volume of a ball of radius r, and that grows slower than a linear function, then we will also be able to find geodesic spheres of arbitrarily small size, and we will also be able to apply this theorem to find minimal hypersurfaces. This 10 here is not optimal. One can do a little bit more careful estimate in various places in our paper and get it down to 3, or maybe if you push even more, maybe you can get it down to 2. And conjecturally, I would think that one can get it down all the way to 1. Okay. So let me now talk a little bit about the main technique and the compact case that's been known since 1980s. Are there any questions about Theorem 3 or Theorem 2? So existence of minimal hypersurfaces in closed manifolds is known since 1980 by the work of Almgren, Pitts, Shane, and Simon, who extended it to high dimensions. If M is a closed Riemannian manifold, then M contains, so let me put the year here, contains a closed minimal hypersurface finite, closed minimal hypersurface, which is smooth away from singular set with Hausdorff dimension of the singular set equal to n minus 7. So appearance of these singularities is related to the fact that even for the solution of the plateau problem for minimizers with a fixed boundary, in the ambient dimension 8, you already find existence of singularities. You have examples of the Simon's cone. So that's the best that you can hope, seems to be the best that you can hope in higher dimensions. And let me quickly try to give you a heuristic idea of how the proof goes. So if you think of a space of hypersurfaces as some sort of an infinite dimensional manifold, which it is not, but let's still picture it that way, and you try to come up with some kind of a mountain pass argument, you start considering families of hypersurfaces, gamma t. So each point here is a hypersurface, which begin and end on a hypersurface below some threshold V0. And then you can, for some reason, for some topological reason, guarantee that as you go from here to here, the area must go up to some value w, like the width that I introduced earlier, then you can start minimizing the maximal area of this hypersurface. You start considering families gamma it with maximum of the volume gamma it going to w as I goes to infinity. So you have these families which get closer and closer to this point w. And then, because you cannot go below w, that means that there has to be an obstruction which doesn't let you pull it down, and that obstruction has to be because you're converging to a minimal hypersurface. So you conclude that there exists a sequence of maximal area hypersurfaces. So they are maximal area in their corresponding families. These points which are high, which are converging to volume W, which converges, and they show that it converges in a certain weak varifold sense to a minimal hypersurface. So this is the kind of argument that we would like to imitate in a non-compact setting. Any questions so far? Okay, so let me introduce some notation. Let's call set U, which satisfies this property, that it has small boundary compared to its width. Let's call such U good sets. And let us now introduce some notation that will be helpful in describing the proof of the result. So the compact case, the proof of that is contained in the book of Pitts and in the paper of Shane and Simon. But it is quite an undertaking to read them, and I strongly recommend someone who is interested in construction of minimal hypersurface using min-max methods to read a simpler proof by Delelis and Tasnadi. I don't exactly remember the year. It's 2010 maybe. So they simplified several parts, and it's quite readable. Okay, so some notation. We will talk about various notions of families, sweepouts, and width. Sweepouts and width. So let U in M be open and bounded. First, we will say that a family of hypersurfaces gamma T, which will all be boundaries of certain open sets omega T, is a sweepout of the set U if following condition is satisfied. The initial set omega 0 intersect U is empty set, and the final set omega 1 contains U. So if this is our Q, then a sweep out could look something like this. This is our gamma 0. It's a boundary of omega 0. And then this is our gamma 1. So this is region omega 0. This is region omega 1, which completely contains you. We will say that gamma t is a good sweep out if it is a sweep out and volume of gamma 0 is less or equal than volume of the boundary of u over 5, and volume of gamma 1 is less or equal than volume of the boundary of u over 5. So the meaning of that definition is that we want to be in a situation like that. We want to start on something which is separated from up we have to go and then comes down, so that we can have a mountain pass argument, and then when we tight it, the ends don't interfere with what's happening as we converge to a minimal hypersurface. And then finally, we'll define something called a nested sweep out. Of u if it is a sweep out of u and gamma t is actually a preimage of some Morse function. So let me state it slightly differently. And there exists Morse function f from m into r, and gamma t is equal to the preimage of this function. So corresponding to each notion of sweep out, we will define a corresponding notion of width, where we will define W of u to be the mean max quantity for all gamma t sweep outs, and Wg of u to be the mean max quantity for all good sweep outs. Gamma t is good. And then of course W n of u will be the mean max for all the nested sweep outs. So the proof proceeds by noticing certain relationships between these three numbers: Wn of t, Wg of t, and Wn of u, Wg of u, and W of u. Any questions so far?
What's the continuity
say that
I
again?
mean, in T you want some kind of continuity, I guess, right? I mean,
That's right.
So when it's a Moss function, it's okay, but in the other situation,
Yeah. So that's a very good point. So the notion of continuity that we use is the same as in the Lelis-Tasnadi paper, where we are considering, where we require that our boundaries of, first of all, the sets are continuous in the Hausdorff topology, but much strongly we have smooth convergence away from finitely many points.
So it's the same.
Yeah. So, right, yeah. So they do look like what you kind of intuitively feel they should look like. And then some component can disappear to a point and disappear. That's what can happen. So the proposition is that 1 for all u, which are open and bounded, we have that the nested width is equal to the regular width of u. It doesn't matter whether you sweep out by hypersurfaces which are allowed to move and go back and forth, or you're only considering sweep outs which are nice level sets of a fixed Morse function, which all are pairwise disjoint. And the second result is that if u is good, in the sense that its boundary is sufficiently small compared to its width, then the good width of u, where we restrict only to sweep outs that start and end on a small hypersurface, is equal to the width of u, to considering or any sorts of sweep outs. Okay. So, in fact, the way we kind of started to think about this problem is that we were interested in this statement. Greg Chambers with Regina Rotman proved a similar statement for curves on surfaces. And we've been trying to see if one can generalize this to higher dimensions and whether one can find useful applications for that. And I visited a workshop on min-max theory in Oberwolfach several years ago, and I discussed this question with Camilo, and he expressed a lot of enthusiasm, and so we started to work on it, and then we realized that there is a connection to the minimal hypersurface problem. So there are basically three things to do. A is to show how proposition implies theorem 3, the main result, which I erased. B, to prove the first statement in proposition, and C, to prove the second statement in proposition. And I feel that I will not be able to do justice to all of these three things. So I would like the audience to choose which one of the A, B, and C you'd like me to do in the remaining time.
Are you supposed to have a vote or what?
Anyone who shouts out the first will be the one I'll follow. Okay. So there are no strong preferences one way or the other.
I can pick one and then you modify.
Okay, sure. Well, I can go in order. Let me start with A. So we would like to imitate the situation in the compact case to prove our proposition. So we have fixed our set U, and we would like to consider sequence of good sweepouts so let me indicate that I'm doing part A. With the maximal volume becoming as small as possible. To Wg of u as I goes to infinity. And then we would hope to use arguments from the compact situation to say that somehow it approaches the minimal hypersurface. So this is our sweepout. And first we notice that the minimal hypersurface of maximal volume doesn't necessarily have to intersect U. So it could be that this is the minimal hypersurface of maximal volume. And then for some later family, which is even closer to the min-max value, maybe this will be the maximal hypersurface, and maybe it will be somewhere there, and maybe it completely escapes into the end. So it does converge to a minimal hypersurface, but that minimal hypersurface happens to be empty, happens to have zero volume. So that's the main difficulty with dealing with something where you want to do a min-max argument in a non-compact manifold. So what would be very helpful is the following proposition. There exists some epsilon which depends on u, which may be very small, but it's positive and it depends only on u, such that for every good sweepout gamma t, there exists some t star such that the volume of the intersection of gamma t star with u is bounded away from 0, and volume of gamma t star is greater or equal than Wg of u. When we have a proposition like that, we can combine it with the arguments for the compact case and show that we will get a convergence, a weak variable convergence to a minimal hypersurface. So that's the main new tool that we need. So let me call that proposition 2. Proposition 1. That would be proposition 2. So how can we prove proposition 2 using proposition 1? Well, so what is a really bad situation when it fails? And we have our region U, and we have our sweepout. Let me use the red again. By hypersurfaces, and we notice that the ones that intersect U in a sufficiently large area all happen to be submaximal. So all of these hypersurfaces have volume less or equal than Wg of U minus delta, just slightly below. Okay. So now we can color this part that they sweep out. And notice that this colored part, which we will call U tilde, has width which is smaller than the width of U. So we have width of U tilde less or equal than Wg of U minus delta. And then we use proposition 1 to go from the Wg of U from W of U to Wg of U. By proposition 1 part 2, we conclude that Wg of U is less or equal than Wg of U minus delta. That means that there exists also a sweep out of that region which starts and ends on some hypersurface whose initial and final hypersurfaces actually have small area. And once they have small area, we are able to push them out of U here and here to construct a legitimate sweep out of U. Therefore, W of U is less or equal than Wg of U minus delta. But that contradicts proposition 1, 2 again, because they have to be equal. So the reason we couldn't just avoid all of that and say, well, why don't we start pushing it out right away? Because we know that we can choose epsilon to be small so that there will be a way to push it out with small increase in the area. Well, the problem is that this delta might potentially be extremely small. It might be very small compared to epsilon. And so if we try to push it out, we may increase it too much. And we will not get a contradiction. Is that okay? Okay. Okay, so B might be a little too technical and not enough time for that. So let me jump to C, unless you want me to B. Okay. Let me jump to C. So here we would like to prove that Wg of U is equal to W of U. In other words, if we start with some set U and then we sweep it out by hypersurfaces which potentially have all very large areas, then we can somehow convert it to a new sweep out which starts and ends on small area hypersurfaces. And by doing so, we will sacrifice only arbitrarily small amount of area. We will increase only by an arbitrary small amount. So we'll construct a new sweep out with initial and final small. Whereas here they're all large. Does it make sense? And to prove that, we will need to use part 1 of the proposition, that we can replace an arbitrary sweepout with a nested sweepout. So step 1, we replace arbitrary gamma t with nested. Now when it is nested, it looks rather nice. These are all boundaries of nested open sets, one inside the next one. And make the following observation. You have to have, for some gamma t in this family, we have to have that the part that sits outside of region U will be small compared to the boundary of U. So there exists some t star such that the volume of gamma t star take away U will be less or equal than W of U plus delta. So here we assume that volume of gamma t's is less or equal than W of U plus some small delta. So we are starting with almost optimal sweepout. And if the parts that go outside of U are large, then what we can do is we can construct a competitor sweepout, which is just taking those families and looking at the boundary of the intersection of the set with U. As a result, we replace this part, which is outside, with the part which is just a piece of the boundary. And because we've been starting with something which is almost optimal, we are not allowed to get something much better by replacing this part that goes outside with the part of the boundary. Because of that, we will get something like that, this inequality. So if this is our T star, then we can look at this set. We notice that boundary of omega t star take away U has size, sorry, I switched to this faster notation, less or equal than 2 times the volume of the boundary of U. So this part plus delta. So this part is comparable to the boundary, and this part is just a piece of the boundary. Therefore, if we consider the set of all open subsets U such that omega 0 is contained in U and U is contained in omega t star take away U. Sorry, I should change this to BV. And then if we minimize among all subsets the size of the boundary, we know that this is less or equal than 2 volume of the boundary of U plus delta. Then we pick a set V in this collection of all sets which are squished between this and the initial omega 0. So these will be our sets V, which almost minimizes boundary area. So we would like to avoid the issues of singularities, and therefore we allow a tiny bit of larger area than the minimizer. So then if we consider set omega tilde t equal to omega t union this V, then what we'll notice is that it will start on V. So its initial area will be small. It will be smaller than 2 volumes of the boundary. And then, because it's a minimizer in a certain region, when you carefully compare various parts of the sets, you will see that this operation does not increase the area at all because of the definition of this as a minimizer. And so this will modify our arbitrary family to a family that starts on something of small volume. And similarly, you can modify it so that it also ends on something of small volume. And what was essential to that is that we have a family which looks like a nice nested family, and we have a particular fixed region where we can do minimization. Okay.
Thank you very much.